Welcome class to chapter 11, where we are going to review the awesome independent samples t-test. So they give an example of you want to know whether self-proclaimed psychics are more accurate than non-psychics. So you have your population of psychics and you have your population of non-psychics, and you're going to compare the two groups. You get a sample of 50 individuals chosen from each population. Each sample completes the card prediction task to provide a mean and standard deviation for each sample. And remember the card prediction task, whether or not they can correctly predict the suit of the cards, which standard would be 25%. And you would expect the psychics to do better because they can perceive the future. So since you're comparing two groups, right, of psychics versus non-psychics, we are looking at independent samples. They are between subjects design, right? Not within subjects design where the same people receive this different treatment conditions, right? Between subjects design is you have different groups and they might be receiving different conditions, or you're comparing two different populations, which I'm going to go over in a second. Comparison of two separate and independent samples. Oh, right here, right? The samples may be drawn from different population where you're comparing the different populations on some measure. For example, college grads versus high school grads on a memory test. Or the samples may come from the same population but exposed to different treatment conditions. And you can, of course, remember the famous college grads on a memory test where one group gets caffeine and the other group gets a placebo. So remember, between subjects design, two groups, you could do some simple random assignment, plopping them into the two groups. Hopefully they'll be equal because you did that, right, on pre-existing variables. And then you run your study. And you are going to use an independent samples t-test, of course. The mean and variability of scores for each sample can be calculated and then compared, right? That's what we want to do, is really compare these two groups to see if there's some statistically significant results between caffeine and placebo group, for example, or psychics in this example, and non-psychics or self-proclaimed psychics. Similar to the paired samples t-test, the numerator of the t-score calculation will contain the mean difference observed between the samples. So right here, this is the mean of the psychics minus the mean of the non-psychics, right? Between the samples, rather than between the pairs of scores, like in the paired samples t-test, right? Where we're taking that different score and comparing the before and after, for example, you're comparing two groups. So it's the same thing, right? Right? It's just a little different. And then you subtract it from 0, which is the expected difference if the null is true. I talked about that in the previous video. And that would be right here. But the denominator of the t-score calculation will contain the estimated standard error for an independent samples t-test. And that's right here, this S sub x minus x2 with a line over it. And that's found slightly differently than for the paired samples t-test because you use pooled variance, which is a term that you use or learned about this chapter, instead of the standard deviation. But as you'll see when I show you the calculations and what it shows in the book, they're just an alternate way to say the same thing, but you're using variance instead of standard deviation. And in this case, a pooled variance, which allows you to get one single variance term for samples that might have different sample sizes. The rest of the steps are the same. Compare the t-score for your study with the t-critical value. And I'm going to go over that in an example in this video. But this is the independent samples t-test right here formula, where you have the means subtracted from each other, psychics versus non-psychics, minus 0, over the estimated standard error for an independent samples t-test, which is this S sub x1 minus x2. So the formula for sample standard deviation, where the sum SS is the sum of squares of the deviations from the mean, you'll recall is this, right? It's the sample standard deviation equals the square root of the sum of squares over n minus 1. And you'll remember that the variance is basically the same thing as a standard deviation, but it's not square rooted, right? To find the standard deviation, we're going to take the square root of the sum of squares over n minus 1. So it's basically the same way to write the equation, right? The reason why the book reviews this is because you'll use the sum of square of the deviations from the mean for your calculation of the pooled variance, right? Which is used in the calculation of the estimated standard error for an independent samples t-test. And the pooled variance is represented by this S sub p and squared here. And it's the combined variance terms for two samples weighted by the sample size of each sample. The pooled variance will be used to calculate the estimated sampling error, estimated standard error, in the independent samples t-test. And it allows us to calculate one variance value, right, for two samples, even if they have different sample sizes. So that's pretty cool, right? We only have to do one, we have one score that we can plug in, and it's called the pooled variance. And this is the pooled variance formula right here. This is the symbol for the pooled variance. And as you'll notice, it's hardly much different than the sample variance formula, right? So the sample variance formula is the sum of squares over n minus 1. And you'll remember the df is n minus 1. So this is the same thing, but we're adding them together to get the pooled variance formula. Okay? So it's really no different than what you've already learned in previous chapters. I think it's in chapter 5. So just remember that. You know, all this stuff is just building on stuff that you already know. It might be a little review, right? So you just review it because you might be feeling a little rusty, right? So that's the pooled variance. You need to find the pooled variance to be able to use that for the estimated standard error for an independent samples t-test. Okay. Now up to this point, we've calculated the estimated standard error, speaking of, right, using the standard deviation. But as you'll remember, the standard deviation is just a variation of the variance, right, which is the square root of the variance. So for a one sample t-test, we can use the S sub x right here, which is the estimated standard error for one sample t-test, right? And we take the standard deviation of the sample and we divide it by the square root of n, our sample size, right? Alternatively, we can write the same thing, the same formula for the estimated standard error right here, using the variance, and then we just take the square root, right? Okay, and this just shows the paired samples t-test. So if you're looking for the estimated standard error for an independent samples t-test, again, now we're going to use, remember, the variance, right? So we're going to use the pooled variance right here. And we're going to add them together over n. And as you can see right here, it's hardly any different, right, than the estimated standard error for one sample t-test using the variance, right? That was the variance written that way, right? It's the same thing, but it's using the variance instead of the standard deviation, and we're pooling it together, okay? And so the estimated standard error for an independent samples t-test is essentially what? It's the pooled variance term. So we find that, and we find that using the sum of squares. So sum of squares is really important. We need to know the sum of squares, n degrees of freedom, of course, which is n minus 1, right? And then we need to know the sample means to compare them to them. And then once you know that, it's just a matter of plugging them in the formula, which I'm going to go over in a second. So speaking of the formula, this is it again, the estimated standard error for an independent samples t-test. That's the symbol right there. And you're going to take the pooled variance, add them together over n, and take the square root of that. Okay? And then you plug in that estimated standard error for an independent samples t-test into your independent samples t-test formula, just right down here. Okay? You're going to subtract the two means, get some value here, subtract it from typically 0, right? And you're going to divide by the estimated standard error. So it's really just no different than what we've already learned with the one sample t-test and that whole thing. And now I'm going to show you an example which will hopefully make a lot of that make sense. Because remember, with statistics, you really just have to know kind of, okay, here's my terms, here's how to find these terms, here's how to plug them in the formula, and here's how to read my output. If a lot of that other stuff, you're just like, well, I'm confused. Well, hopefully it's just building upon, remember, what you already know. You already know about how to find the estimated standard error for one sample t-test, but now we're using the variance, which remember, instead of the standard deviation, which remember is not the square root of the variance, right? But which is the standard deviation, but you're using the variance. So step one in terms of taking a look at this experiment. You have your alternative hypothesis. In the population, the difference between the condition means should be greater than 0, and note that this is a one-tailed test. The null hypothesis in the population, difference between the condition means would be less than or equal to 0. And of course, the population mean for psychics will be higher than the mean for the population for non-psychics, right? And so it will be greater than 25%, as we found in the results. And the null hypothesis is the population mean for the psychics will be lower than or equal to the mean for the population of non-psychics. Okay? As is typical for behavior research, we will set our alpha level at 0.05. And in this study, we ended up with 45 psychics who attended and 50 non-psychics who attended. And you'd think, okay, 50 psychics said that they were going to attend, and then they didn't attend. You think they would have known ahead of time. Maybe they just weren't courteous. They knew ahead of time. They weren't courteous and told the experimenters that they weren't going to show up. But they didn't show up. Or maybe they showed up and, you know, they didn't report it in the text. In any case, so you have the N of psychics is 45 and N of non-psychics is 50. So how are you going to compare these two when they're different sample sizes? They're pretty close, so that's great. And remember, we can use pooled variance. So that's the whole meaning of that discussion right there. And so what am I plugging out right here? I'm plugging out all the values that you need for the t-tests. Because like I talk about with cooking, for example, where you have you know, all of your things, your vegetables and everything that you need all chopped up and ready, and then you're ready just to throw it all in there. It's good to have everything that you need ahead of time. And so you're just like, kind of like, okay, take a deep breath, just a matter of plugging in these values, finding my t-score, done this before, comparing it to the t-value of a one-tailed or two-tailed on my t-table. Or plugging it into SPSS and just getting that easy p-value, right? In any case, if you're hopefully doing this by hand and SPSS, these are the values that you need. Your N, your mean accuracy for both the psychic condition and the non-psychic condition. So it looks like the psychics performed a little better at 26% than 25%, which was the non-psychics. But it really doesn't look like that significant of a score, 26 versus 25. I mean, come on, really? You think that they do a little better. Of course, we have to look at the standard deviation and see how tight the standard deviation is, or of course variance is what we're using now, but how tight the data is or how big the data is in terms of standard deviation. If it's tight, it's going to take you less to get to the finish line. Remember what I talked about, that t-critical score? But if the data is a lot of variance, saying like, okay, some people, you know, some psychics did really well, but some didn't do so well, then you got to question the whole self-proclaimed psychic thing, right? Or whatever that you're comparing. So the psychics' mean accuracy was 26 versus 25. For the non-psychics, the sum of squares in this example, they didn't make you find the sum of squares of the deviations from the mean. They gave it to you, sweet, right? Which is kind of a pain to find, or takes you a little time to do that, is for the psychics is 550, and for the non-psychics is 350, okay? So there's a little more variability there for the psychics, and this is the data that you need, essentially what I just went over, right? The sum of squares, and degrees of freedom, which of course is 1 less than n, and the mean scores for each group. Then it's just a matter of plugging in the data into the equation and finding out if your t-score is a rare score in the distribution of sample means, right? If it's super rare, it passed that finish line of t-critical scores, right? High t value over, whatever it is at the 0.05 for one-tailed or two-tailed. And if it is, then you reject the null, right? That default action. The data makes our default action look extremely ridiculous, right? Or if not, then you fail to reject the null and you basically say you learned nothing. So step 4 is we're going to calculate the statistics, and remember this is just a little piece of that big flowchart, but hopefully that flowchart is just coming more and more a lay of the land that you're understanding, and you're going to be comparing means. How many sample means to? Is it a between subjects or within subjects design? It's between subjects. You're going to use an independent samples t-test because you're comparing 2 means versus 3. 3 is going to be an ANOVA, which you're going to learn in the next chapter. Woohoo, it's pretty fun. And so here I have the example of the steps you're going to take. Really simple in terms of doing the independent samples t-test by hand. First, you need to find the pooled variance because you're going to use the pooled variance in your estimated standard error. And then you need to find the estimated standard error for an independent samples t-test in order to plug in that value for your independent samples t-test. The pooled variance is, as you recall right here, for both groups is 550 plus 350, right, for the psychics and the non-psychics. And the degrees of freedom is 44 and 49, because remember you subtract 1 from the n. That gives you 20.93. Add those, divide. Plug in 20.93 now, which is this, right? Your pooled variance. Plug it in here. Boom and boom. What's the n? You already know that. 45 and 50. Boom and boom. What's the estimated standard error? Remember this symbol right here. Read it over and over, study it so you really remember it. I think that's what's helpful too in making this stuff less overwhelming. Okay, just plug in the values that I need and know what the symbols mean, right? And know what the formulas are. And so you plug in 20.93 here and here. And you plug in 45 and 50 here and here. And then what we do is we add up these and take the square root. And so essentially that is 0.94. And then you calculate your sample t-value. So this is your t-test right here. You're going to subtract the means, remember, from the psychics versus the non-psychics. They didn't do that much better, right? Apparently, right? And subtract it from 0. So you basically have 1 over 0.94. What is 0.94? It was the estimated standard error that we found, remember, right here. Plug in 0.94. Remember, it's just a matter of plugging in the values, right? We found our pooled variance, which was needed to find our estimated standard error for an independent samples t-test. Then we put in the independent samples t-test, 26, 25, 0.94, boom, 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 and we get a t-value of 1.06. And then remember, for the degrees of freedom, in this example, you're going to add the degrees of freedom for both the samples, both groups, to look up that on your t-table. Okay? So the total degrees of freedom is what you're going to find, which is 44 plus 49, which is 93. And your t-critical value for a one-tailed test, right, remember, with the degrees of freedom of 93 is 1.658. Okay? And the sample t-score, remember, of 1.06 does not fall in the critical region of the distribution, remember? 1.658 is the finish line. Did we get there? No, we stopped short. We didn't go in the rare scores over here, which we kind of thought, right? 26 over 25 doesn't really make our default action look ridiculous, right? It really doesn't, or it seemed that way. And our t-test showed us that at the 0.05 probability level. sample score of T of 1.06. It's not greater than that, so it doesn't fall in the critical region, right? So what we say is we can't reject the null hypothesis. It didn't go into that, critical region. We fail to reject the null hypothesis, and what I like to say is we learn nothing. Just a note about using SPSS to conduct the independent samples t-test. Of course, SPSS is super cool, right? Once you learn it, just plug in the values, just boom, right? Just have to know how to read the output, right, of SPSS and follow some assumptions and do the right tests, statistical tests, right? And then you have the power, right? You have the power within you, or to be able to tell people, statistical results and stuff, and sound really fancy and intelligent. So how to read the SPSS output? You'd be like, no problem, give me that SPSS output. I'll tell you what it's all about. Note the 2 rows of data. 1 row, 2 row. I just blew this up so you can't see the whole thing, but this is your output of the most important data. Okay. So 1 row and 2 rows. The equal variance is assumed row, and the equal variance is not assumed row. And note the Levine's test of equality for variances right here. If the Levine test is significant, notice the sig right here, which it's not. It's 0.154. Okay. That's not below 0.05, of course. If the Levine test is significant, then use the second row for your t-score and p-value. Okay? T-score and your significance. Okay? Make sense? In this case, you're not going to use the second row. You're going to use the first row because the Levine is not significant. And then remember, the SPSS output gives you the p-value for a 2-tailed test. And if you want the 1-tailed test, you're going to have to divide your p-value by 2. Just going to make it smaller, and smaller is better in this case. Test assumptions, the population of different scores. So in order to be able to use this test, right, there's some assumptions that you have to meet. The population of different scores must be a normal distribution. This allows us to use the t-distribution table to find our t-critical value. And the scores from different participants within each sample must be independent. The scores from the different individuals within each sample cannot be related in some way or another. And then a new test assumption that you're learning excuse me, for this chapter is called the homogeneity of variances. It's an assumption of between subject t-tests and ANOVA's analysis of variance that the variance in scores in the population is equal across groups. In SPSS, you can use the Levine's test for this assumption is provided. And that is it for independent samples t-tests. Hope this was helpful, and see you next week for ANOVA.